Okay, so what I'm going to present now is some slightly more complicated models that in my group we applied to HIV infection, okay? But they're closely related to what you guys already worked. So, all right, so just remind you of the natural history of HIV infection, yeah? So we have the early peak in viremia, yeah, and then a decay, and then we reach in kind of a steady state for a while, and then something happens at the end when the patient gets AIDS. Okay. And I'm repeating myself a little bit just to remind you, we have very effective therapies against HIV infection. They don't cure you, but they prevent you from getting sick, and they also reduce onward transmission to other people. If you apply the therapy early, you get very good results for most patients. Okay. Later on, I'm going to talk about what we briefly discussed yesterday, which is prophylaxis. So taking medicine before you're even exposed or immediately thereafter to try to prevent the risk of, to reduce the risk of infection. Okay, but as discussed yesterday as well, you can have side effects from the drugs. There is potential for drug resistance to emerge, and they can be quite expensive. Okay, so I'm going to talk about actually 3 projects. Okay, so this slide is out of date. I'm going to talk about viral load dynamics during long-term therapy. Okay, and then I'm going to talk a little bit about early infection. All right. So, as I've already showed you twice, we have some interesting information from treated patients, which is that they can have viral blips. Okay, so a patient on stable drug therapy drug therapy can still experience periodic resurgences in their viral load. Yeah, it's on now, isn't it? Okay, it's weird. It's sort of a nonlinear response, right? Okay, all right. So we have patients with viral blips, all right. Okay, so what causes the viral blips? So people came up with hypotheses for where the viral blips came from. Could it be that these people who experienced viral blips weren't taking their treatment? Well, there's no actual evidence for that. It's possible, but there's no real evidence for that. Could it be that they had another infection which caused an expansion of immune cells in their body to fight the secondary infection, which then led, now there's more targets for the HIV, so perhaps you're getting, there's more targets for HIV, you get a transient increase in the amount of HIV that's present. Again, not really much evidence for that. Okay, and is it possible that it's just assay variation? And yeah, probably sometimes it is, but there's way more of it than you'd expect, just given assay variation. There's a very nice paper from the lab of somebody called Nettles in the US where he really looked at detailed viral blip information, and basically he doesn't see no evidence for anything except this is an intrinsic property of patients who are on antiretroviral therapy. Okay, but in any case, why is there any virus left at all? Okay, so why is there any virus left in a patient who's on a treatment that knocks out the viral life cycle? So you saw in the exercises yesterday that you have antiretroviral drugs that can basically prevent replication. So where is the virus hiding? Okay, so you saw this yesterday as well. So where's the virus hiding? Latent cells, right? So the model from yesterday afternoon was that the virus is hiding in the latent cells, okay? And the latent cells are long-lived. They're not producing virus at any great rate, so they don't become targets for the immune system, because there is an immune response to HIV, so they would be killed if they were really producing viruses. So the virus is just hiding there, and periodically a latent cell will activate and produce some virus, okay? So when we found out about that, we decided that we could make a stochastic model based on latent cells. And that model is more or less the model that you studied yesterday afternoon. Okay, so this was our model for HIV latency. Okay, all right. So the latently infected immune cell reservoir is about 1 in every million So what's that, 10 lakh? 1 in 10 lakh, I love it, T cells, or CD4 T cells will be a memory cell. Okay, there are most of the latent cells are memory T cells, but there are probably others. Okay, and the latent reservoir builds up during the pre-treatment period. So during that period of very high viral load, the latent reservoir kind of gets filled. Okay, and then when you're on treatment, the evidence is that the latent reservoir will slowly decay with a half-life of a bit less than 4 years. Noisy. There's variation among different people for what that half-life is. Okay, some people don't even look like their latent reservoir is dropping at all, but some people it's a little faster. The average is maybe 4 years or so. Okay, so our hypothesis for the viral blips was that they're due to the activation of latently infected cells. Okay, and so this was our model, and you'll sort of recognize this. So we have latent cells, which are dividing at some rate rho, that are dying at some rate delta L, and that periodically, well, randomly will become activated, yeah, at rate A. Does this look familiar? Yeah, you saw this yesterday, right? Okay, so the first problem was just to look at L, yeah, and then problem 2 was to look at L and T star. Okay, now I'm not going to make you guys do the full model. You don't also have to do V. The problem when you do V is there can be a lot of virus and it can get slow. Okay, so just helping you guys get results reasonably quickly. I'm not giving you the V to do. But it works just the same, right? So the T stars are the actively infected cells. They're producing some viruses. The viruses get cleared out. Okay, so that's our model. Okay. We also considered a model where the drugs are not 100% perfect. Okay? And if the drugs are not 100% perfect, then it's possible for a free virus in the model to make a new infected cell, or even perhaps a new latent cell. Okay? So we could look at this as like a more intricate model where the drugs are not preventing completely new cells being infected by viruses. Okay, so this is a more advanced model. It actually doesn't make too much difference which model you use. Okay. Is the second model kind of clear? You understand what I'm talking about? If you've got drugs, you basically cut out this arrow, so the viruses can no longer produce new latent cells. Yeah? And you cut out this arrow, which means that the viruses can no longer produce new actively infected cells. Okay? Make sense? Okay. All right. So just looking at the simpler model, we can write that as a system of differential equations and solve it. Yeah? And it's really, really boring, as you can imagine. If we just plot the virus, V, as a function of time, all I get is an exponential decay. Yeah? This model is actually linear, and it has 3 eigenvalues. And the eigenvalues are delta, C, and this thing, which is controlling the decay of latent cells, rho minus A minus delta L. Okay? And this is kind of slow, so this is controlling the long-term decay to having no viruses present at all. Okay? So if you do the linear analysis on this, there's only one fixed point, which is at 0, where everything is 0, but it just takes a very long time to get there from any kind of reasonable initial condition. Okay? All right. But if we go with the master equation model or the branching model, so this is still the simple version, right? Okay? I can write down all the reactions for this. So L goes to T star goes to T star plus V, L divides and makes 2 L's, yeah? So that I can write down all the reactions for this, and then, hey, what do we call that? What's this? Forward Kolmogorov master equation thing, yeah? Yeah, okay. Do you believe that? This is actually forward. Sorry. Well, P is the solution. Hold on, is this forward or backward? This is forward. This is forward. Okay, this is forward. Okay, this is the forward equation. So this would be the forward master equation for this thing. Sorry, I don't know why I'm confused. This is forward, okay. All right, so based on this, we can then simulate. So does this look familiar at all? This is what you made yesterday, right? Yes. Yeah, I'm actually plotting the viruses, yeah, because I have the viruses in my model. And the viruses is what you would measure in an experiment, yeah. But you can see that you get this noisy decay. The yellow line there is the mean, which we can calculate, yeah? And so we can do this. Okay, all right, and what am I showing here? So this is one run. This is averaging 4,000 runs just to make sure that we converge to the analytic mean, and we do. So the blue line here is average of 4,000 simulations. The yellow line is the analytic mean, okay? And we can plot a distribution of how many viruses per milliliter does this correspond to in a patient, okay? Now, if you say that a viral blip happens, this is at some fixed time, okay? If you say that a viral blip is happening over here, you can see that the viral blips are rare events. So even though I did 4,000 simulations, I only found 150 viral blips at one particular time, yeah? So they're actually quite unusual. And by the way, we biased the parameters here to have some viral blips. But this is not a good way, running Gillespie simulations is not a good way to calculate the probability of seeing viral blips. Okay, does that make sense? Because they're quite unusual. So your Gillespie simulation spends a lot of time sort of in the average viral load, and just occasionally will take a jump high enough to be recorded as a blip, and that will be short-lived, and then it will go back. Yeah? So
you're saying that this is a shortcoming of the algorithm rather than just that this is a model that doesn't include the phenomenon?
I would say if you want to study a rare event that occurs in the model, so the model includes the phenomenon, yeah. But if you want to know about the proportion of viral blips, so if you took a random patient who was following this model exactly, and you measured their viral load, if the probability of a viral blip is, say, 1%, then if you do, if you do a bunch of Gillespie runs, you rarely see, you only see viral blips in 1% of the time for any of the patients.
But if you were to go much more than 4,000 simulations,
you would see some, but then it starts to take a really long time to simulate too. So the point is that just simulating isn't the way to explore rare events, or it's an expensive way because you spend an awful lot of time simulating not rare events, and you're really interested in the rare events. So it's not a good way to capture rare events by Gillespie simulation. Yeah. So just to summarize, this is a very exaggerated picture. Okay, but with the blips, the things you're interested in are happening in the tail of the model, yeah? So it's happening in the tail of the distribution, and so Gillespie just doesn't find them all that often, okay? Make sense? So this is 4,000 simulations. Would you say I've gotten the probability distribution very well defined here? No, it's very lumpy still, right? I have to do 4 million, or not, maybe not 4 million, but especially to accurately understand what's happening in the tail, I have to do a lot of simulations. So how frequently I hit the tail. So simulation is not, for this question, a especially effective way to go. I mean, you can do it, it just requires waiting a long time for your computer to run. Yeah? So what we did was we wanted to go back to the master equation and do things analytically. Okay, so we wanted to analytically calculate that tail rather than simulate that tail. Okay, so that's the goal here. And I'm just going to do the things that we did this morning, just it's going to be for a 3-part model rather than a birth-death model. Okay? All right. Okay, so we can derive the backward equations. So here here is the backward equations. Okay, so we can derive the backward equations similarly to how I derived them for the birth-death model. Okay, so do you see that the probability now is the probability of having L latent cells, N T stars, and V viruses? Do you see that? So it's a 3-dimensional probability, and there are 3 initial points, L, N, and V. Actually, I think the things with the bars on top are the initial conditions, and the ln and v is the dynamic thing. But yeah, okay. All right. So we can get these, and you just have to grind through triple summations. Okay. So you're summing over all possible l's, n's, and v's. Yeah. So you grind through this thing, and you can get it. Seriously, writing it down is not a good idea because I'm going to change the slide before you can write all those subscripts. Okay, but the idea is this is the equivalent to the backward equation that I had this morning. Okay, now this is the probability generating function for the three type process. So we have three types of objects. We have L's, T stars, and V's, and the probability generating function then therefore has to have three variables: X, Y, and Z instead of just Z, and it still has time in it, same as before. Okay, and it's the summation of X, Y, and Z, each to their own powers, yeah? The powers correspond, so X is kind of the latent cell variable, Y is the T star variable, and Z is the virus variable. Okay, so for my three-type process, I sort of have a three-way generating function, okay? And same as before, if we want to calculate things, we can do this. So to calculate the mean number of viruses, so the V, the average of V, we want to find out V times the probability, right, and sum that, yeah? Okay, so it's just dg/dz, yeah, Z is the virus variable, okay, evaluated at X equals Y equals Z equals 1. Yeah, so I can still pull things out of the generating function the same as before, I just have to be careful to partial derivative in the correct direction, okay? Okay, and we can also calculate, for example, what's the probability of having V virions? So the probability of having V virions at time t, same as before, 1 over V factorial, V derivatives of this thing, yeah? Does that make sense? And evaluated at the correct point, where X and Y are equal to 1 and Z is equal to 0. Okay, so it's very, very similar to what we were talking about this morning. If you have the generating function, you can calculate the moments, so the mean and the variance and stuff, and the individual probabilities of different events. Okay? Does that make sense? Yeah.
Is there a problem with applying this, given that your V might be very large?
Yeah, I'll get to that. That's very prescient of you, but yeah, I'll get to that, yeah. The question was, is there a problem if you have a large value of V? So you have to take a large number of derivatives. The answer is yes. So I'll get to that, okay? But yeah, I'll get to that. All right, so if you do the same thing again from this morning, so you take the generating function and you kind of, multiply your equation by x, y, z, or x to the L, y to the N, z to the V, and then, sum it up three ways, and up over three variables, what you get is some huge thing that I don't even want to put on the slide, okay, for your generating function equation. Yeah, so now you have your generating function equation, which is an infinite system. No, it's a system of infinitely many differential equations. Okay, but then if you apply the independence and the identical independence assumption from this morning, you see how it's all exactly the same as this morning? Yeah, you apply the identical independence assumption, which is essentially that if you have L cells, that's like having one cell to the power of L. If you have N cells here, that's like having one cell to the power of N in the generating function. Exact same thing that we had. Then you can break that infinite dimensional set down into three nonlinear equations. So you remember we had our Riccati equation at this point, yeah? For the one type problem, it was a Riccati equation. For the three type problem, we get these three nonlinear equations. Now, if you're a pure mathematician, at this point you stop because you can't solve. It's not Riccati, so you can't solve it, okay, so you give up. Okay, but what do we do when we see nonlinear ODEs? How do we solve them? You guys are back to being quiet again, come on. How do we solve nonlinear system of ODEs? Fixed points Jacobians, you could do that. What would be the lazy man's approach? Numerical, okay? What technique could you integrate these with? Numerically. Fourth order Runge-Kutta, yeah? Okay, if anyone ever asks you that question, just say fourth order Runge-Kutta, okay? All right, so you can integrate these things. You know, MATLAB has what's it called, ODE 4.5? Yeah, ODE 4.5, right? So you can use ODE 4.5 to solve numerically for these generating functions. So then you get numerical solutions of the generating functions. Fantastic, yeah, that's great, yeah, we can do that. Right? No reason why not, yeah, with appropriate initial conditions. The initial conditions are the X, Y, and Z. Now that's what we talked about this morning. The initial conditions are the other variables, X, Y, and Z, yeah, but we can put in different values of X, Y, and Z and build up, because we know the time dependence of the generating functions. Using different values of X, Y, and Z, we can figure out how the generating functions go in time for any values of X, Y, and Z that we should wish to have. Okay? Make sense? So it's a little bit technical, but we can do it. And we're clever, so we can numerically integrate, right? We can do these things numerically. Okay. All right. Now this is really only going to make sense to the people who've done complex analysis. Because there's a problem, which unfortunately I didn't write on the slide. The problem is a viral load of 50 copies per milliliter in a human who has 5 liters of fluid. Okay, so if there's 5 liters of extracellular fluid in a human, okay, so 5 liters is 5,000 milliliters times 50, 5,000 times 50 is 5,000 times 10 is 50,000 times 5. It's 2.5 lakh. Yes. Okay? All right, I love this. It's 2.5 lakh viruses. So can you take 2.5 lakh derivatives of this thing? No, it's impossible, right? Yeah, you can't. If you try to numerically differentiate 250,000 times, it's very, very unstable. Okay, so you don't differentiate. What you do is you apply complex variables. So we want to figure out the probability of having a given viral load at a given time. Yeah. So we know the generating function tells us how to do that, right? This is the formula from the generating function. Okay. So the Cauchy integral formula. Do you remember this? Raise your hand if you've seen Cauchy's integral formula. Come on. Okay. Good. All right. Cauchy integral formula tells us how to take n derivatives. Yeah. It's you put an n plus 1th order pole in the middle of your complex plane, and then you integrate in a circle around it. Okay? So we can integrate like this, and basically we end up then, so this is my complex circle, okay? And this is the thing that always shows up when you apply Cauchy integral formula. So and it's in this position because we're interested in the viruses. So what I can do now is I can numerically integrate this thing. So how do we numerically integrate this? What algorithm could be used? How do you numerically figure out what definite integrals are? Yeah, you can use Euler's method, or what's a little better than Euler's method? Simpson's method, or 4th order Runge-Kutta. Yeah, or what we actually did was we decided to use trapezoidal rule because it seemed to be working reasonably well.
Which is Euler.
No, trapezoidal's one better than Euler. Euler is just rectangles, trapezoidal is
Linear interpolation.
Linear interpolation, yeah. But you could do any of these methods. These would all work fine. Okay. The only thing is you have to calculate these function values you have to calculate quite a lot of these function values, but you do that by solving your nonlinear system of differential equations. Yeah? So what you do is you run ODE 45 quite a lot to solve. We didn't actually use ODE 45 in the end, but the principle stands. You run ODE 45 a lot to get the function values, and then you run trapezoidal rule or Simpson's rule on top of that to integrate and get your probabilities. Okay? And it works beautifully. It works beautifully. Okay? And it also makes you feel clever because you did complex variables and numerical analysis and generating functions, and somewhere there's some HIV model. So you feel good about the whole process, right? Yeah. Okay. So this is our algorithm to calculate the distribution of viral loads, which includes these rare events that I said are hard to get to by simulation. Okay, so what you do is you solve your differential equations up to your desired time, okay, with initial conditions that you like. Yeah, so you have your initial conditions on some range, which is a circle in the complex plane, okay, and then you calculate your generating function and then you numerically integrate. Okay, so I know I said I was going to do it analytically, but this is pretty close to analytical, right? I'm not making any approximations other than what I'm introducing through the numerics. Okay, and I know, because I'm reasonably good at numerical analysis, I know how big the errors are that I'm introducing with each step. Yeah, so if I want to improve my error, I know that I have to take, you know, more steps in my Runge-Kutta method or more points in my trapezoidal rule. Yeah, make sense? Yeah, we did do convergent studies. You have to be a little bit careful. And just full disclosure, this function here actually oscillates quite a lot. It's actually quite oscillatory. So because the function's sort of doing that, we actually did adaptive integration where we picked more integral points to map out the oscillations. And then some parts where it's quite smooth in other parts of the complex plane, we were able to use sparser points there. So we did some things to try to improve this. But numerically, it runs a lot faster than doing a whole ton of Gillespie simulations. A lot faster. Yeah. So we can calculate all kinds of things. This is actually from the homework from yesterday. So this is, for the 3-type model, this is the latent cell time to extinction. So you guys were computing this numerically, right, in problem 1? Yeah? So for the 3-type model, but actually it's just the L's that control the latent cells, all this is irrelevant. So you guys numerically did this. We calculated the distributions. Okay? You could also calculate the distributions. It's just a birthday process. Okay? But we find, for some different parameters in the model, we find different distributions of times to extinction, for example. So, you know, you can see for different parameters that we pick, we can calculate that some people should be cured of HIV after 20-some years of perfect antiviral therapy. Now that has not happened. So what reason do you think there could be that the latent reservoir seems to still be around, why people are not being cured by being treated for a long time? Anyone have any ideas about that?
Resistance.
Probably not drug resistance. Different values of rho, yeah. Or to put it another way, the latent cell reservoir is not just one kind of cell. There are probably some short-lived cells and some long-lived cells and some medium-lived cells. And the estimates we have for latent cell decay are probably dominated by the loss of the short and medium long-lived cells. The ones that live for a really long time probably do not die in a human lifetime. So this may actually be too simplified of a model. So given better information about different kinds of latent cells, we might be able to come up with a better model which would better fit what's being seen. Just a little story here. So I heard a talk by an immunologist, and at some point in his life he kept a monkey colony. And he infected the monkeys with, let's just say monkeypox. I have no idea what he infected them with, but he infected them with something in such a way that he could detect the memory B cells. Okay, now 20 years later, he went back and he looked, the colony had to be closed down, so he basically autopsied monkeys and looked for the memory B cells that were from that infection from 20 years previously, and they were sitting there in the bone marrow of the monkey, and they hadn't divided. The original, he had a way of telling if they divided or not. The original memory cells were just sitting there 20 years. So it's quite possible that we have memory cells in our bones or elsewhere that are memories of things that we had as children, you know, as young children even, you know. And this is very bad news if you're trying to kill off the latent cell reservoir, because you have cells that could live 60 or 100 years. Anyway. Okay, so yeah. So even if this was true, the clinical message is still kind of depressing, that you have to take drugs for like essentially probably the rest of your life, and then there's a small chance that you might be cured by the end of it, right? We could also look at this thing that I asked you to look at also in the homework, which is transient viral extinction. So when the number of latent cells gets low, it's possible that there's no viruses around sometimes. So the latent cells are low enough that not enough of them are activating and producing viruses. So you end up with transient viral extinction might be happening after, say, 20 years. Okay, so this is also in question 2. When you get to question 2, you'll see this, yeah? Okay. All right, and then the thing I was talking about before, we could calculate the probabilities of seeing a viral blip as a function of time. So all of these graphs are for different parameters that we wanted to investigate, because we don't actually know some of the parameters, so we were trying out different sets of parameters. But essentially, as time progresses, you go from having, this is your viral load distribution, you can see the blips will be up here, and as time progresses, it gets less and less likely that you should see a blip. Okay, so these curves are taken at 1-year intervals, okay, for I think, 10 years or something like that. Okay, and it's different for different parameter choices that we made. Okay, so if we actually knew all the parameters, we could do a much better job and sort of fit. As it was, what we did was explore the space. Okay. Now, okay, so this is all a very triumphant message in a sense, right? I mean, the results may not seem all that interesting, but the math is very nice. So I did math, and I'm proud of doing all that math. So then we wanted to know, if you see a patient who has a blip, how long does that blip last for? So imagine the viral load is doing this, yeah? And then occasionally it goes up to the blip level, and then how long does it stay up there for? So it turns out that you cannot, from the probability distributions, figure out how long things take. You can figure out the probability of being there now, and the probability of being there next, a week from now, but you have no idea if that's the same blip that stayed up high, or in fact this one over here is a new one that came up. So actually, to figure out blip durations, we went back to Gillespie simulation. Okay? But now, because we're starting our Gillespie simulations in the blip state, in the high viral load state, every simulation gives us a data point, essentially. Right? So what we did was we started our simulations with a high viral load, and we waited for it to drop back down again. So that's how we could do the simulations, and we could figure out what's the typical sort of blip duration that we expect to see. So this is actually a prediction now. If you wanted to, if you could find patients with blips, you could then ask them to come back the next day and measure their viral load and see, do you see blip durations of around, say, 2 or 3 days? Okay. We could also calculate things about blip amplitudes and reproduce this plot over different parameter choices. Okay, so just to summarize the latent cell model, stochastic models are essential to study this because deterministic models don't capture what you want to see, what you're interested in looking at. We came up with some really great numerical methods to find the probability generating function, and we also did Gillespie to simulate the dynamics. This model gives you a clearer view of what's going on with latent cells and how the approach to extinction might happen than previous differential equation models people had used. Okay? And we generally think it's possible that small blips of the kind I showed you could be driven by stochastic fluctuations, but stochastic reactivation of latent cells producing kind of a burst of virus. But if you see really large blips, we never see those in the model. That tail of the viral load is still not really big. And occasionally patients have viral blips which are really high, like 1,000 copies per mil for one measurement. And that must be something else that we don't capture in the model. We can't get that from this. Well, we know how it would fail, right? Okay, so if we know the expected convergence rate, right? So if you take if you take evenly spaced trapezoidal points with a gap h between them, then the error is supposed to be order h squared, right? So if you take h goes to h over 2, so you make your grid twice as fine, yeah, then you know that there's a prediction of how much it can. There's a prediction of the convergence of the method as a function of the grid size.
But it's a bit more subtle, right? Because it really depends on the actual form. If you have a lot of positive curvature, you tend to overestimate.
No, the error doesn't. The error still scales as h squared as h goes to 0.
Right.
Yeah. Yeah. So because we were using sort of well understood explicit methods, we understood how the error should behave.
Right.
I mean, all these error estimates are only valid for h small, and I suppose it's possible that h wasn't small enough, but that's always something, you can always criticize convergent studies on that basis.
Yeah, I guess it's just like if you have an oscillator, you're just integrating a sine function, and you will have a rational fraction of the step size to the period, then you'll get perfect results because you'll have as much overestimate as underestimate.
Yeah, that's sort of a weird
if you have a thing where your positive curvature, you get a bias in terms of overestimate.
You do, but as you reduce your h, excluding your sort of resonance effects when you have an oscillatory function, but for general function, as you squeeze the h down, you should predict that you'll appear to be approaching something at a rate of h squared.
Right.
Okay. So if you get consistent results in that sense, then you generally have a good sense of how big your error really is. Oh, you have an estimate of how big your error is. Yeah, so this is a benefit of using simple methods, is the error estimates are also simple. If you use complicated methods, the error estimates might not be quite so easy to interpret. Yeah.
And then just one other thought on this is that could there be something about what's the mean concentration of infected cells?
We measure in the blood.
Yeah,
it's measured in the blood. So
if you're measuring in the bloodstream close to where it passed through an organ or something with a high.
Yeah, I think people generally feel like the blood is reasonably well mixed, although I'm actually not sure quite how well mixed it is.
Yeah.
So I suppose you could sample at somebody's foot and somebody's finger.
But it might be that in some people the finger's worse than in some people's foot.
Yeah, it could be. But you look for correlation between the different blood. Yeah.
Question related. Is there any organelle where that cells could be more?
Yeah, so you would expect that there would be a lot of T cells in the gut, for example, in the thymus, in lymph nodes, and generally patrolling the body. But there's certainly, they find HIV-infected cells just about everywhere.
And anywhere you've recently had an infection.
Yeah, I guess, yeah, if you cut yourself, you would expect some T cells to be there to clean up any bacteria, well, anything that came in there, maybe, yeah. I mean, you're more broadly, there's a question of whether we've got the right model. I'm not aware of any better model than this. Some people have done a refinement on this model where they have two different tissue compartments, one where drugs penetrate well and one where drugs don't penetrate as well. That's quite interesting, but I guess I would think that that's sort of a just different version of our model. And is our model completely wrong? Do latent cells not behave in this sort of general way where they divide and get activated with constant rates? And that's where more experiments could come in and really help us out with the modeling. Yeah. Okay. All right. Now I promised you guys one more thing. So one more thing you will have. Okay. So do you remember? We were talking about estimating the window period. So estimating the time between getting infected and having detectable infection. And I remember I showed you that you had, that we could calculate the conditional generating function. And in fact, it's problem 3 that you're supposed to work on. Okay, so in problem 3, you're supposed to calculate a conditional generating function for a birth-death process. So the model that we decided to apply to this data is a conditioned version of this. So we didn't apply the simple birth-death process that is problem 3. We decided we were going to work with something slightly more complicated where we had infected cells and viruses. Okay, so the infected cells produce viruses and the viruses produce infected cells. Okay, and both things get cleared out. So there's a death rate for the infected cells, which is delta, the death rate for the viruses, which is C. Okay, and so we built the stochastic version of this model. Okay, there are things that we could make better. I don't know why that's on this slide, sorry. There are things that we could make better about the model, but this is the model we went with, so everything's constant rates. We're not doing time delays and time varying immune response or anything like that. This is the model. It's as you understand it from that picture. Okay. And what we could do was we could apply. Have I got the wrong slides here? No, these slides are messed up. Sorry, but anyway, I think there's enough here that I can explain it. Okay, so what we could do here is we could calculate. So this is for the simple birth-death process. So the slides are slightly messed up. Sorry. For the simple birth-death process, we could calculate the condition generating function, and then, as in problem 3 that you guys are doing, you can calculate the mean. So we can do the same thing, except for the two-part model. And rather than calculating analytically, we again have to solve a system of differential equations first. Okay, but we can do that. So we do that. Okay, and what we do is we fit. So this is again showing the birth-death model, not the two-part model. But for the birth-death model, you can still imagine having the conditioned mean and the unconditioned mean, and we fit the conditioned mean. Okay. Oh, here it is. Okay. So here's our generating function, which is a two-dimensional generating function, yeah, with a Z1 and a Z2. Z1 is for the T star cells, and Z2 is for the Vs. So you can see the summation over the probability, Z1 to the N, Z2 to the V. So we have N cells and V viruses, okay? And then if you generate the backwards equation, plug in the generating function, and do this, then you get this system of nonlinear differential equations that we solve numerically. Okay, and from that, we can calculate the mean. Okay, so we can calculate the conditioned mean of the two-state model, the same way that you guys will calculate the conditioned mean of the simple birth-death model. Okay, all right, and then we can fit the mean. So, for example, the red here is the data for patient 6243. Okay, so the red here is the data. And we take kind of a weighted average of where the initial slope of the growth in the viral load data, and we fit the mean of that using the condition model, and we get an estimate of that the patient became infected on day 5 1/3 or something like that. Okay, time 0 is their first negative viral load measurement. Okay, so we estimate that they were infected here. They had negative test results here and here because their viral load was too low. And then they had a first positive out here at day 17. So we would estimate a gap between here and here of about, for this patient, about 11 days before we would have been able to detect their infection after they got infected. Okay? And if you don't apply the condition model that gives you the bend here, yeah, then you would basically come out and you'd estimate another 3 or 4 days of additional time before the infection was detectable. So, you know, I don't know if that's really important or not, but we like doing it, you know, and I was happy to do it. And I think it's an interesting thing to think about as well, that you have to condition your model to reflect the fact that everybody in your data gets infected, right? Okay, so we could do that for a whole bunch of people, and then we could plot for each of, this is just 32 patients, we have about 85 patients or 100 patients that we actually use, and you could plot here the probability of being infected if you had a negative test that day as a function of the time since you might have got infected, okay? So you can basically see the probability of being infected drops off for each patient, so each gray line is one patient, and it drops off until, if you have most patients, if they had a negative test on day 30, we could say pretty confidently they're all negative. There's a few of them that appear like they might be infected they might have had a very slow growing infection. That's just part of the data, right? There's a spread, there's a difference between the different patients. The red here is the average. Okay? So if you like averages, you could say, on average, if you get tested 35 days after you might have become infected, then you have your risk of infection is down to 5% of what it was originally. I mean, your overall risk of infection is not that big. You know, single risky event is just not that. We estimated it as 0.3%, okay? That's from independent estimates, that's not to do with the data. But so you can see that your risk, despite having had a negative test, drops off very rapidly after about 10 to 12 days. So I promised you I'd show you that, right? Does that make sense?
Yes. It's just separately. So when I first looked at this, I was thinking that the line at the top would be about the prevalence in the population, separately from
No, there's epidemiology here. Patient, one risky event, and then how does the probability that they're infected, even though they just had a negative test result, how does that change? Yeah. And this is generally in keeping, I think, with how most physicians would behave. They'd give a patient who came in a test immediately, or they'd refer them for a test immediately, and then they'd suggest they would have a follow-up test, say 1 month or 2 months later, which seems to be very, conservative way of dealing with things. Yeah. Okay. All right. I think that's the end of the lecture because you guys are all looking unbelievably sleepy. So we'll stop there for now, and the plan is it's 3:25. So why don't you try to work for half an hour on completing the problem this afternoon, okay? And then there'll be a tea break, and then you can go back to it for a little bit before Samit gives his talk, okay? And I'll be around to talk to you guys, okay? Great, thank you.